In today's video, we will talk about probability generating functions. Probability generating function is just one of the four main ways of getting moments. A quick reminder, you can either directly use the definition of expectation to find moments, okay, and when you do so, all you have to do is just solve this integral. For when you're dealing with continuous distributions, you times the PDF by x and you solve this integral, it should give you the first moment. Now, probability generating function only works for discrete distributions, and we'll see shortly that when we derive the probability generating function g of z, when we try to do something with it, i.e. differentiate it and then evaluate it at 1, we are not going to get pure moments in the sense that we are used to work with. Okay, we would like raw moments, but unfortunately, we're gonna get factorial moments out of the probability generating functions. We can see that there will be a way around it, and we can actually transform this probability generating function slightly to get raw moments. Okay, another way is the moment generating function. I discussed this already, and just for completeness sake, this is just the expectation of the e to the power of tx. Working with moment generating functions easy. You just differentiated this moment generating function and evaluated 0 to get your nth moment. Yeah. So the derivative that you will be taking of this MGF will decide on the raw moment that you will be recovering from this expression. Okay, then the last one, we haven't covered this yet. It's coming. It's characteristic function. The good news is it always exists. Unlike the moment generating function, which doesn't always exist, characteristic function always exists and is very similar to moment generating function. It's an expectation of e to the power of itx. Okay, so if we were to draw some similarities between the two, then the only difference is this imaginary number I, which obviously stands for square root of -1. Now we also can differentiate MGF, times it by -I to the power of the derivative we are taking, then evaluate this expression at 0, and we will get the nth moment. Okay, time to actually see what probability generating function is. Okay, I will quickly enumerate all these properties, and then we'll just apply it straight away using Bernoulli distribution as an example. Okay, so here the definition of probability generating function is expectation of z to the power of I, where I is the our random variable. Okay, it can take any number from 0 to infinity, so it's a sum of all z raised to the integer, okay, and then times the probability associated with the this integer. It may sound very technical at first, but there's nothing complicated here. We'll demonstrate it a couple times, and hopefully this will be clear. So properties of probability generating function: you can actually differentiate this probability generating function times 1 over I factorial, evaluate at 0, and this will give you probabilities that are linked with the integer. So if, say, I want to know what's the probability that my random variable will take a value of 2, well, then I have to get the second derivative of this probability generating function, evaluated by 0, and times it by 1 over 2 factorial. G of 1 is just 1, okay, because all it says is if I sum all my probabilities associated with my random variable, okay, then I will get 1, because it has to sum to 1. So for instance, regarding property 2, if I have a random variable which takes 1 or -1, say coin tossing heads or tails. If it's heads, it's 1. If it's tails, it's -1. And the probability associated with this random variable, taking minus 1 is 0.5, and taking 1 is also half. So the sum of these two random variables, the probabilities associated with the two values that this random variable can take, is 1. Okay, so that's what property number 2 means. Third property of moment generating function is that if you differentiate this function, which is just an expectation of z to x, well, you will get x times z to the power of x minus 1. So for instance, we've got z squared. What's the derivative of this? Well, it's 2z 2 minus 1. Yep. So that's just very easy property. Just when you differentiate something, well, you have to decrement the power, put it here, yep, and there you go. But an interesting property is property number 4, which says if you differentiate the probability generating function once, i.e. to take the first derivative, and then evaluate it at 1, you will get mean. It is kind of easy to see because when we replace, so when we differentiate, which we've done here once, and we evaluate it at 1, so z equals 1, here our z is going to equal 1, and when z equals 1, then this whole expression here that I'm highlighting, it will drop out, it will just be 1. So that's an interesting property. Now, property number 5, we would have thought that if we just take the second derivative and evaluate it 1, we'll get a second raw moment. But unfortunately, and this is where I don't like really working with probability generating functions, because when we differentiate twice, we are getting something like this, yeah, which almost looks like a variance, because if only the second term was squared, we would have a variance. But unfortunately, we've got a second moment minus the first moment. So we still have to work pretty hard to actually find out what the variance is. It's not as intuitive. It's not as easy as working with moment generating functions. And this term here, which I just underline, is called the factorial moment. So when differentiating probability generating functions, you're not getting raw moments, you are getting factorial moments. Okay, and this is shown here in property number 6. Okay, and look at the last term here. What it says is that when you differentiate, when you take any derivative of this moment generating function, I stands here for the derivative, your last expression, your last term in your expression will be x minus I plus 1. I is just the derivative, yeah, and this whole thing is called ith factorial moment. So straight away, we don't like working with factorial moments because this is not something we can relate to. We need raw moments. So the thing is, how are we going to cope? Because how for instance, how are we going to get variance out of a probability generating function? Well, let's remind ourselves that if we differentiate twice the probability generating function, we'll get something like this. Okay, so we have to be smart here. What can we add to this expression here from 5, okay, to get what we want, to get the variance? Well, if we just keep the second factorial moment, okay, which is e x squared minus e x, if we add to it the first moment here, which was the first derivative of the probability generating function evaluated at 1, okay, so that's what we've done. We keep here the second factorial moment, we add the first factorial moment, i.e. our mean. Well, if we do this, then guess what's going to happen? Well, this term will drop, and then we subtract first factorial moment squared. Okay, first factorial moment is exactly the same as mean, so we will eventually arrive at variance. But it's kind of complicated because we first have to take the second factorial moment, then we have to add to it the first factorial moment, and then subtract first factorial moment squared. it's kind of, I don't like, personally I don't like working with this. So, is there any better? Yes, we can do better with probability generating function. This expression comes to our rescue. You will soon see that if we just differentiate the probability generating function and multiply it by z and then evaluate it at z equals 1, we'll get the raw moments. So we can actually slightly modify the differentiation of the probability generating function and get what we want, i.e. raw moments. Okay, so in this video I presented the properties of the probability generating function. In the next video I will show all these properties using Bernoulli probability generating function, and then I will do another video shortly on Poisson distribution. Both of them are discrete distributions.